The James Webb Space Telescope has photographed something spectacular, a brief but powerful blast of energy bursting out of Proxima Centauri, the nearest known star to our solar system. The flash, fleeting but mind-boggling in intensity, has left astronomers amazed and brought a whole new level of complexity to understanding stellar activity. Proxima Centauri, a red dwarf star just more than 4.2 light-years from our planet, has had a reputation for its mercurial nature for years. Its regular outbursts and explosive periods have been documented for decades, but the size and nature of this new flare have taken well beyond the scientific community's existing expectations. In the grand scale of cosmic fireworks, this was rather less a spark and more a blinding explosion, a tantrum of a star whose consequences might ripple through planetary science, exoplanet habitability research, and even the hunt for extraterrestrial civilizations. The discovery was made in the course of an ongoing but very focused survey Webb has been doing on nearby star systems. This specific mission is aimed at examining the atmospheres of potentially Earth-like exoplanets by tracking their host stars' energy output and activity over the long term. Proxima Centauri in its natural position occupies the top position in terms of priorities, not just due to proximity, but due to the fact that it harbors at least 2 known exoplanets. Proxima b, the more interesting of the two, orbits inside the habitable zone of the star, where liquid water might possibly be present on its surface under the appropriate circumstances. The second, Proxima c, is a bigger and cooler world that orbits further out, in an area unlikely to harbor life as we understand it. As Webb's collection of instruments detected the unexpected flash, it was anything but normal. The burst of energy was so intense that for a couple of seconds, several sensors were overrun, prompting onboard systems of the spacecraft to automatically shift data acquisition modes to avoid damage. The optical and infrared wavelengths both recorded stinging, needle-like spikes, the type astrophysicists recognize as indicators of exploding events immediately. But it was not a conventional stellar flare, it was a blast of unprecedented energy that took less than the time it takes to boil a cup of tea to unfold. Within slightly less than 3 minutes, Proxima Centauri unleashed a burst of energy tens of thousands of times more powerful than the biggest ever recorded solar flare from our own sun. The initial response among astronomers was one of exhilaration and trepidation. Proxima Centauri's flares are not just an academic curiosity, they are a key factor in whether its planets could sustain life. The star's reputation as a flare star, prone to intense and unpredictable magnetic activity, has always complicated the otherwise tantalizing vision of a habitable Proxima b. But this event has raised entirely new questions. Was this an isolated superflare, magnitudes more powerful than ever before coming from the star, or does it point to an entirely new class of stellar activity that models can't yet account for? Might it even indicate a transition phase in the magnetic evolution of the star? The initial in-depth study concentrated on the spectral signature of the flare, and what was revealed was strange enough to get eyebrows raised right around the astrophysics community. The outburst had a layered, multiplex composition of ultraviolet and infrared light, topped with patterns of energy that did not fit the typical templates of recognized red dwarf flares. In the majority of instances, events like these eruptions are produced by magnetic reconnection events, where jumbled magnetic field lines in the star's atmosphere break and instantly realign, releasing built-up energy in an explosive burst. On our Sun, these phenomena cause coronal mass ejections and solar storms. But in the flare of Proxima Centauri, scientists detected both intense thermal radiation and a surprising level of non-thermal emission, the latter implying that particles had been accelerated to velocities close to the speed of light. That particle acceleration put its own signature in the data. Webb found bursts of synchrotron radiation, light produced when charged particles curve along magnetic field lines at relativistic velocities. This is a feature more typically seen in the tail of a supernova or the maelstrom surrounding black holes, not in tiny, cool stars like Proxima Centauri. The existence of this radiation indicates that the flare was not only a superficial surface phenomenon, but possibly involved more robust magnetic structures running through the outer layers of the star. Perhaps the most fascinating and cause for concern was the directional nature of the flare. Rather than spewing outward in a radial sphere, the energy appeared localized along a small beam, similar to a jet. Math shows that this jet was pointing inward toward the interplanetary system at the time. If Proxima b was in the way, the implications would have been dire. A direct impact by such a focused blast would strip away huge chunks of an atmosphere unless a planet's magnetic field was incredibly strong. Even if the air remained intact, its upper layer's chemistry might have been altered entirely, forming transient compounds that are biosignal-like. For astronomers searching for evidence of life, that would be an annoying complication. Biosignatures might show where there isn't biology, or vanish completely if wiped out by the radiation of the flare. Follow-up calculations revealed that the flare's total energy output was equivalent to unleashing the combined energy of millions of Earth-scale nuclear detonations every second for its brief duration. To put it in perspective, our Sun's largest recorded flares are powerful enough to disrupt communications on Earth and damage satellites. Proxima's flare was tens of thousands times more powerful, and it erupted from a star with barely 1/8 the Sun's mass. Such an inordinately large energy release is not only impressive, it's on the verge of being daunting to any would-be fan of life in Proxima's system. Ground-based observatories were promptly notified by an automatic early warning network, and telescopes ranging from Chile to Hawaii mobilized to trace the fallout. These follow-ups offered useful ancillary data in optical, radio, and X-ray wavelengths, but none equaled Webb's resolution and sensitivity. Orbiting at the second Lagrange point, some 1.5 million kilometers from Earth, Webb has an unobstructed view without the distortion of the atmosphere. That position enabled it to record faint emissions following flares that had disappeared within hours, signals that would have been completely lost from the ground. This one event has already started to reshape the discussion about the habitability of planets orbiting red dwarfs. Such stars are the most abundant in the Milky Way, comprising approximately 3/4 of the stars. Many have small, Earth-like planets in their habitable zones. But if such superflares are the norm, they may pose an impassable obstacle to the evolution or persistence of surface life. For Proxima b, recurrent exposure to such bursts of energy over geological time could strip away its atmosphere, dry out its surface, and sterilize its biosphere. Any life there may have been pushed underground, protected below layers of rock or ice from the incessant barrage. But there's another explanation, that this flare was not a one-off freak occurrence, but part of a longer magnetic cycle. During the days leading up to the flare, Webb measured slight changes in Proxima Centauri's brightness and emission spectrum, too small to be detected without careful, long-term monitoring. They could be the stellar counterpart of foreshocks before an earthquake, a warning sign for magnetic field realignment. If that's the case, astronomers would perhaps one day be able to forecast such outbursts, a development that would revolutionize the way we assess the stability of exoplanet environments. There's also the issue of what the flare did to the space around Proxima Centauri itself. The star is bathed in a thin coating of dust, gas, and perhaps icy debris from comets or planetesimals. The burst of high-energy radiation might have ionized some of this material, triggering shock waves that radiate through the system. These disruptions could even impact the orbits of small bodies or change the appearance of light from Proxima's worlds when viewed from Earth, making it difficult to study their atmospheres. Perhaps most urgent is the question of whether Proxima b possesses a strong enough magnetic field to protect it from such stellar aggression. Earth's magnetic field is one of the several reasons life has endured here despite the Sun's periodic outbursts. It shields charged particles and keeps from large-scale atmospheric stripping. Without that shield, even a fairly mild flare can inflict devastating damage to a planet's atmosphere over time. If Webb or subsequent missions can spot shifts in the ionosphere of Proxima b or changes in its reflectivity following flares, it may provide the first indirect indication of an extraterrestrial world's magnetic shield. Reconstructing the timeline of the flare has been an unprecedented stellar forensics exercise. Webb's instruments monitored the event from the initial flash of ultraviolet, through the burst of near-infrared and X-ray power, and into the extended, waning tail of cooling plasma. Each stage stripped back a layer of the star's internal layers, providing glimpses into how magnetic energy is stored and released in such small stars. The reaction has already been likened to capturing a volcano erupting on another planet, except the lava in this instance was a jet of radiation traveling almost at the speed of light. Aside from the astrophysics, the ramifications extend into the search for extraterrestrial intelligence. If there is intelligent life on Proxima b, this flare would have been an epochal event, one probably chronicled in whatever history or mythology such life forms would have. Alternatively, flares such as this one can present galaxy-wide challenges for civilizations around unpredictable stars, potentially compelling technological progress toward radiation shielding and planetary defense. For SETI scientists, knowing the frequency and nature of such flares might dictate where and how they scan for signals, preferably quieter stars where life would be less likely to be ravaged. On a larger cosmic scale, the flare provides a valuable real-time laboratory to probe magnetic reconnection, which continues to be one of the grand challenges of astrophysics. Although we recognize that it drives solar flares to the most massive and intense explosions in the cosmos, the physics behind how magnetic field lines disconnect and reform in extreme conditions is not very well understood. Witnessing such a process occur in a nearby star, at Webb's unprecedented resolution, provides theorists with a wealth of information to hone their models. Even how the flare affected Webb's own instruments has been instructive. The first burst of energy overpowered specific detectors momentarily, leading engineers to investigate new calibration procedures for coping with unexpected high-energy events. This is raw science, not just adding to our understanding of the universe but feeding straight back into the equipment used to study it. What began as a routine stellar monitoring session has turned into one of the most compelling astrophysical mysteries of the year. The data from Proxima Centauri's extraordinary outburst will likely fuel research papers for years to come, each peeling back another layer of the event's complexity. Whether it turns out to be a fleeting cosmic hiccup or an omen of more regular stellar tempests, this much is certain: the James Webb Space Telescope has reminded us again that the universe is much more dynamic and much more unexplainable than we could ever have dreamed.